We do the tutorial 3, which is on cement. I told you at the very beginning, here in this subject you have two parts. One is material design part and the other one is the structural design part of the pavement. So first 5 weeks you are learning about different materials, material properties, and how to do the material mixing part. So concrete mix design and also bitumen mix design, asphalt mix design. And other 5 weeks after this one, you have the structural design part, and that will be on structural design of the flexible pavement and the structural design of the rigid pavement. So last week we discussed about the aggregates, am I right? So this week we are looking at cement. So cement is the binder that we use in the rigid pavement to bind the aggregates together. And when we add water to cement, cement is reacting and that will becoming hardened. So that the hydraulic cement, but we have non-hydraulic cements as well. So if I summarize the things that you have learned in the lecture, you have learned about the types of cement. So we can broadly say hydraulic and the non-hydraulic. As I have mentioned before, hydraulic is the cement which get hardened when you add water. Non-hydraulic cements getting harder, not reacting with water, but reacting with something else, like, for example, carbon dioxide. So we need non-hydraulic cements in rare situations, like, if you do a construction in a water environment, then we don't want the cement to get hardened by reacting with the water. So in that kind of situations, we need a non-hydraulic cement. And also you discuss about the early strength gain, low heat, sulfate resisting. So we have different types of cement with these different properties. So we will do some questions, so you will be okay after doing the questions. You already also learned about the production of Portland cement. Portland is a trade name, and cement is manufactured using limestone. It's a natural product, and we break it and we burn it to 1400 degrees Celsius in a kiln, so it will become clinker. Then we grind it to a powder, and also we add some admixtures and we are getting cement. And also you have learned about this chemical compositions. We have actually questions on this one. There are 4 main compounds in cement. Do you guys remember those 4 compounds?
Cement, water.
That's the compound, or else the ingredients in a concrete mix. We are talking about the cement, just the cement. No? C2S, C3S, have you heard of those names? Yes, so those are the 4 main compounds, and they are responsible for different properties. So we will learn about it and we will do some questions. To find out how much from each of these compound we have in a particular cement, we are using these equations to calculate that. So we have one question with using the equation, so we will learn about it. And also you need to know hydration of cement. That means what is happening when you add water to cement. So there are few reactions happening. So it is an exothermic reaction. That means it is generating a heat. And we need to know how the strength is gaining with the time. And also we need to know how much of heat is production mainly. There are other things as well. So you have a question in that as well. You need to know the properties of Portland cement and also the admixtures that we can use to improve the properties, to get the desired properties, and also sometimes to reduce the cost. We use some admixtures. Okay, so these are the things that you have covered in the lecture 3. Do you guys remember these things? Were you in the lecture? In 1 hour class, we won't be able to cover everything. So they are very important. You get my MCQ questions in your quizzes and the final exam. So it is very important to learn everything, because MCQ questions are like, covering the whole part. So you need to know everything. Now, mainly cement, I told you. Cement is made up of limestone, which is a natural material. It has calcium carbonate and the calcium oxide, and also we add clay, then other materials like gypsum, fly ash, slag, to reduce, sometimes to improve properties. For example, to improve the fineness of the final cement product, and also sometimes to reduce the cost, we are using other materials, and also to improve the reaction part as well. And also I told you we need to burn the limestone to make clinker, and it is a very energy consuming process because we need to burn it approximately up to 1400 degrees Celsius. So it's a very energy consuming process. Okay, so that we know. So this process, I think you have it in better in your lecture notes. So I'm not going to go through this because you have them in your notes. Okay, so there are 4 main compounds in cement. This is the common formula. At least you need to remember this: C3S, C2S, C3A, and C4AF. So C3S stand for tricalcium silicate, C2S stand for dicalcium silicate, C3A for tricalcium aluminate and tetracalcium aluminoferrite, this one. So the chemical formulas you can see here. And also if you find the percentages of each of these, mainly in a cement we have C2S, 45 to 60%, but we can't say exactly this many percentage. Different cement has different percentages of C3S. And C2S again 15 to 30%. C3A is 6 to 12, very less, and also C4AF also 6 to 8. We can't get rid of any of these ones. They are like, you know, by burning clinker, burning limestone and making it clinker and grinding, we get all these oxides together. So it's happening due to the reaction. So we can't, like, you know, we can't control much the process. So we get all 4 ingredients in a cement, but in different proportions. For example, if you consider A and B, these two have different compositions of these 4 ingredients, these 4 compounds. Makes sense? We can't say every cement has the same amount of C3S. It can be different, but ranging from 45 to 60%, roughly. Are we good? Any question? And these 4 compounds are responsible for different properties. So if you look at C3S, C3S is contributing to early strength gain. So if you have a cement with high C3S compared to a cement with low C3S, the cement with high C3S is gaining strength quicker than the other cement, because it is, when we add water, it is reacting quicker and the reaction is faster. And C2S is contributing to late strength gain. So if you have, when you compare 2 cements, if one is having more C2S, that one is getting delayed, the hydration is getting delayed. Okay, you have questions, that's why I am summarizing this. When it comes to questions, I want you guys to find the answers. So I'm summarizing the theory part, but you need to remember this stuff when we are doing the questions. C3A reacts with water, can lead to rapid setting called flash setting. So gypsum is added to regulate this reaction and preserves the workability of the cement. So we don't want the concrete to quickly, we need time for the mixing, isn't it? And also for transport. So we are adding gypsum to prevent this flash setting. And also C3A is undesirable. Why is that? It is reacting with sulfate. If we have a sulfur-rich environment, for example, if you are building something in a contaminated land where you have sulfate, or else if you are doing any construction in a sewer plant, sewer area, or else in a sea or the marine area, then the concrete is reacting. This one is reacting with sulfate, and when it reacts with sulfate, it will make the concrete swollen. So we don't want that to happen. We have to. Concrete cancer is a bit different. I will show you that part later. So this is like due to the reaction with the sulfate, C3A and the sulfate reaction, it will make the concrete swollen. Then we don't want that to happen actually. We have to, like, you know, we can prevent it. We can manage this situation by having selecting a cement with less C3A and also having some admixture to manage this situation, or else again, what else? we can have AI entrained concrete to manage this situation. I will talk about the AI entrainment later on. And C4AF is responsible for early setting, accelerate, hydration. However, these two are, however, this amount, if you look at, I showed you in the previous table, these two percentage wise, these two are very little in a cement. Even though this one is contributing to early strength gain, as we have a very less amount percentage, it's not contributing to any strength. Actually, it is gaining a very little strength after the reaction. Are we good? Any question? So hydration of cement means when you add water to cement, how these four compounds are reacting, and that process we call the hydration process. So the hydration is making the cement harden concrete. It will make the concrete. And you have this in your lecture notes. I want to show you two main things. If you look at the strength gain of C3S and C2S, you can see ultimately they're both reaching the same strength. And these two are not contributing to any strength compared to C2S and C3S. However, if you compare C3S and C2S, you can see in 28 days, this one is gaining about 50% of strength. But C2S, we told that it is delaying the strengthening process, or else it is delaying the hydration process. However, it's not affecting the ultimate strength that, like, you know, it will still bring us the same strength, but it is take longer. Makes sense? Sometimes we need to accelerate the hardening process. Sometimes we need to delay the hardening process. When we need to accelerate the hardening process, what kind of situations? When we need to get the strength quickly, yes. What kind of situations? Yes, so mainly if you are, what's that? Yes, if you are repairing a busy highway, you don't want to close that part of the highway for a long time. So you use a cement with more C3S. And also, if you are working in a winter day, because the environment is cold, it will take long time for the reaction to happen. So you need to accelerate it. So we can have cement with more C3S. Whereas, so if you are building a high-rise building, again you need to make, like, you know, the flows quicker because you need to finish it. So in that case also we need the cement with more C3S. Where we need to delay the hardening process. What kind of situations? If your mixing plant and your project is so far, you need the time for the delivery, isn't it? So you don't want the concrete to get hardened on the way. So you need to delay the hardening process. And also, if you have your formwork very complicated formwork, you need time to pour the concrete to that unusual shape, isn't it? So likewise, and also if you are working in a hot summer day, you need time for mixing, pouring, vibrating, compaction. So we need to delay the hardening process. So in a hot summer day also, we need to delay. So these two, having these two is one thing. So, and also we can add admixtures to fasten the reaction or delay the reactions. Have you heard of these admixtures? You can have a cement with more C3S to get the early strength, and also you can add admixtures. So what do we call those admixtures which accelerate the hydration? It's in your notes. Accelerants. If you add accelerants as admixtures, that will contribute in early strength gain. What admixtures that we can add to get the late strength gain, delay the strength gain? What do we call them? Have you heard of retardants? You have them in your notes, am I right? So retardants, we can add retardants. And also, if we have a finer cement, it is reacting quicker. So the fineness also contribute to strength gain, early strength gain. So if you have finer cement, that will gain the strength quicker. It's same as like, you have caster sugar and the normal sugar. Caster sugar is dissolving quicker, isn't it? Because the surface area is high. So likewise, if you have a cement with tiny particles, then the reaction is faster. Okay, the other thing is the heat generation. So this reaction is exothermic. That means it is generating a lot of heat. So you can see the most heat generation is by C3A and then by C3S. However, as we have less percentage of C3A, mainly the heat generation is happening because of C3S. So if you have more C3S in a cement, that will produce as a huge heat. So we may need to add admixtures to control this, to manage the heat depending on our application. Okay, so any question? Now I have summarized the whole lecture, I think, most of the lecture. I want you to answer this question. I have already told you this stuff. So can you please write the answers in your books or the tablets or whatever you are using. What are the names, full chemical formula, and the abbreviations of 4 major compounds in Portland cement? We talk about the 4 major compounds. If you don't remember the chemical formula or the full name, at least you should have remembered the abbreviation which I have told you. So please write that, at least the abbreviation, and tell me, write which one is contributing to early strength gain, which one is contributing to late strength gain, and also you can write about the other two as well. One is undesirable, which is reacting with sulfur. Yeah, so can I give you a few minutes for you to write this? So what did you write? So we have tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrate. So they are the compounds, and we have the chemical formula. You have this in your notes as well. At least you need to remember this thing, okay? So I already told you these things. C2S, C3S, C3A, C4AF. So what they does? Can you tell me C3S is responsible for what? Responsible for what? Early strength development. How about C2S? Late. And C3A? Undesirable, because it is reacting with sulfur and it makes the concrete swollen. And yeah. So any question? No questions? C4AF is accelerate the hydration. However, the percentage is very less, so it's not, even though it is accelerating the hydration, it's not contributing to strength gain. Actually, I showed you the table, the chart. Okay, did you write this? Can I move to the next question? Okay, so I'll give you, okay, so this one actually, I haven't seen this question in any of your quizzes or final exam, because these reactions, it's hard to remember, but I don't know this time whether it will be in any of your quizzes or final exam. However, you have this in your lecture notes. What are the primary chemical reactions during the hydration of Portland cement? Write down the full chemical formula of the hydration products. You have this, you have a slide. So you have this slide in your notes. So you can see C3H stand for H2O, or the water. So you can see they are making hydrants, and also this is very complicated, else it's like, you can see these ones, whatever the products are, again reacting with water, and it is like, it's good if you can remember, but it's a long many reactions, and it's, yeah. So you have this in your notes. If you want to write down, you can write down. Otherwise, you have this in your lecture notes. I think you guys are fine with this. You have this in your notes. Am I right? Yeah. And also, like, the previous slide was with abbreviations. If you want to put the right exact names, it will be like this. But you don't need to remember any of, I'm not sure whether you will get it in the quiz, but it's hard to remember, but you have that in your notes. You can see, yeah. So it's making hydrates, and also, like, the hardening is happening with these reactions. Okay, now we should know how to find the amount of C3S, amount of C2S, C3A and C4AF in a cement. Because we discussed earlier, these four compounds are responsible for different things, isn't it? So if we want to select the right cement for a given application, we should know how to find these percentages, 4 percentages. Depending on, so when we have the cement, we can send the cement to the lab and we can find out the percentages of these oxides in a cement. If you know the percentages of oxides, we can find how much of C3S, how much of C2S, how much of these 4 we have. Okay, so do you have this with you? Okay, so we'll move to the question. So our question is, which of the following 2 cements, cement A and B, will you recommend for repairing a busy freeway? So if you look at these oxides, they look very close to each other, A and B. Silicon, SiO2, we have 24% and 22. If you look at calcium oxide, 61 and 66. So they are not that different oxides. However, to recommend a cement for repairing a busy highway, what we are expecting in repairing a busy highway? Yes, early strength, isn't it? So which compound among the 4 is responsible for early strength? C3S. So we need to find how much of C3S in A and how much of C3S in B, and which one has the higher, we can recommend that for repairing a busy highway. Am I right? So can I give you a few minutes for you to find it? Okay, you have the equations and you have the oxides, and I want you to find not only the C3S, I want you guys to find the C2S as well, due to a reason. I want to see whether you have understood the reaction, so the equations. So can you please, if we have time, actually you can find all 4, but maybe, yes, at least these 2, C3S and C2S for A and B. You have all the equations here. So I want you to find the C3S and also C2S. If you have more time, you can do for the other ones as well, for A and B. Okay, I'll give you time, and when you finish, let me know. Did you find the C3S? When you find the C3S, let me know. So this, I'll make this also to red. So what do we get?
For C3S, cement A is 14%.
Okay.
13.9.
Yeah, 14.
And for cement B, I got 61.43.
61 roughly, okay. Okay, so how about others?
CS2, C2S.
Yes, so what?
C2S cement B is about 18.25. And cement A was 60.64.
Cement A is?
60.64.
I want to check one thing. So what did you put here?
2.87.
What this one? This part here is your C3S. If you go to your formula, at first question we did about the chemical formula, am I right? So this part here, 3 times calcium oxide, silicon dioxide, that is it. That is, this one is your. Do you agree with that? This is your C3S, which you found as 14 and 61. So you need to substitute that. Did you do that?
Yeah, that's what I did.
Okay, that's good. Yes. So that, do you understand what I mean? So here it is, you are not going to substitute from the table, okay? You need to substitute from your previous results. So C3S. For A it will be 14, for B it is 61. So you are substituting that for that part. So what did you get? What did you say? 60.6 for A and B is 18. 18, okay. 18 and 61 roughly, okay. Do you all get that? Now can you tell me, in the question they are asking if we are recommending a cement for early strength gain or else repairing a busy highway, we need to find a cement, select the one among the two which can gain strength quicker. Am I right? Which cement is gaining strength quicker? Which one? B. Yes. Why the B? Because it has a higher C3S. When you look at this oxides, you won't be able to find it because they're very close to each other, all the oxides. But when you put them in the equations, you can see B has 61, A is just 14. So B is gaining strength quicker than A. So we are recommending B for repairing a busy highway. How about if you do a construction in a maybe your mixing plant is far away from your project. A, why is that? You want to delay because you need the time for mixing and transporting. Okay, so I hope you are good with that. Any question? No questions? Okay, let's move to the next one. So we already discussed this. We got the same numbers and we are recommending B for repairing a busy highway. That's good. Okay, next question need more information. I will summarize this part. So there are different types of cements. So there are ASTM standards as well, but here these are the general, like, you know, the names that we use. If you go to Bunnings, you will find different types of cement. Quickset cement, likewise. So general purpose cement is the type GP, and that is used for almost all the general applications. General purpose limestone cement means what? You have all this in your notes. We have an amount of limestone. So cement is made up of limestone. We already discussed that. So when you burn the limestone, this will become clinker. And I told you this process is taking a lot of energy. So we can add some limestone before, like, you know, without burning to the cement to reduce cost, and also it is for rendering purpose. We don't need much strength, we need the smoothness. So limestone, having a percentage of limestone is better for rendering purpose. So when we have some limestone added to the cement, that we call the general type GL. And also we can have general purpose blended cement, where you are blending cements together to get improved properties. And also there are special purpose cements. You can see them in the Bunnings. So high early strength cement to gain the strength quicker. I told you how can we achieve the high early strength? You can have a cement with more C3S. What else? I told you this at the beginning. You can have a cement with more fineness, finer cement, isn't it? When you have a finer cement reacting fast. What else? You can have a cement with an admixture with, we call them accelerants. Am I right? So you can either either have like any of these oils all three together in a cement to have the high early strength. Agree or not? If you have more C3S, or else if you have a finer cement, or else if you have accelerants added to the cement, they all contribute to early strength gain. Low heat cement. So low heat means what? Why the low heat is important? Low heat can be heat generation. I showed you. Most the heat is generated by C3S and also C4AF, isn't it? So this, apart from this one, so why the heat is generating? When this is reacting with water, that reaction is exothermic. That means it is generating heat. Why we need to control this? Sometimes we need to control it. Why?
You can cause cracks.
Cracks. So how the cracks occurring?
What do you mean?
Why the heat generation making cracks?
It's not settled yet. Like, it's not towards its full strength, probably.
And also, like, when we heat up any material except water, it is expanding. When we cool down, it is contracting. Thermal expansions and contractions, with the temperature changes. So this heat generation is only at when the reaction is happening. So it is cooling down after some time. So we sometimes need to, when we have a massive concrete, for example, a dam, we have a massive concrete. So we don't want the dam, especially outer surface of the dam is getting hardened quicker, but inside you have the wet concrete. So it is getting contracted when it is get hardened. So we have these thermal expansions and contractions. Due to that, the concrete will crack. Crack is right, but we need to know why it is cracking as well. So sometimes we need to control it. We can control it by having admixtures to control the heat. Or else we can have a cement with less C3S as well, like, to control it, but like, we have admixtures for that. And sulfate resisting cement. Where did I say the sulfate? Yes, sewer, or else maybe contaminated land, marine construction. So they have sulfur. So sulfur is reacting with what? C3A. So we should have sometimes purposely select the cement with less C3A, or else maybe a cement which has admixtures to control this reaction. And also, when we have sulfur in the environment, we need to have air entrained concrete. So what do you know about the air entrainment? You have this again in your lecture notes. What do we mean by air entrainment? When we mix concrete, even though when you are mixing a cake, you can see the air bubbles trapped in the mix, isn't it? So that air we call the accidental air. So they are staying in lump sum in different places of the concrete. This is undesirable. So it affects the strength. So we need to get rid of this accidental air. So we vibrate and we compact when we pour in concrete. But sometimes we have to purposely add air. This air, purposely adding this air, we call the air entrainment. So this air is evenly distributed throughout the concrete. So why we need to purposely adding air in the concrete is weakening the strength. But sometimes we need to do that to get rid of other issues. So what kind of situations we need to do this?
Also, water passing through.
Yes, so whenever you want to make a porous concrete, yes, you have to. But there are some issues with other situations. For example, if you have sulfur affected area, I told you the concrete is getting swollen. So we need to provide the space for the concrete to expand, otherwise it will crack, isn't it? So in that case, we have to have a iron trained concrete. Again, if our concrete is in the freezing environment, we need to have iron trained concrete. Why is that? Water trapped inside the concrete, when it getting like in the cold environment, it is becoming ice. So ice has a more volume than water, isn't it? Am I right? Have you experienced that? If you fill a water bottle and if you put in the freezer, the lid will come out, or else it will pop up, because when the water becoming ice is expand. The volume of ice is more than the volume of. That's the only material when we cool down, it is expanding. That's the only material, water. All the other materials, when you cool down, it is shrinking, and when you heat up, it is expanding. So when we have a concrete in a freezing environment, we should let the concrete or the water to the space. We need to provide the space for water to become ice. So we need to have air entrained concrete, because it's going through that cycle, freezing and thawing, freezing and thawing. So apart from having a cement with less C3A, we also need to have air entrainment done whenever we are doing a construction in sulfur area. So when you do the structural design part, you need this information, and that's why you are learning it at this stage when you are learning cement. And also you can have shrinkage limiting cement. So we need to limit the shrinkage, because when the reaction happens, concrete is getting expanded because of the heat, and when it is cooled down and get hardened, it will shrink. So sometimes we don't want the concrete to shrink. For example, if you are making a bridge, you don't want the bridge to shrink, right? So you need to have that length. So we need to control this shrinkage. So we have to have a cement with shrinkage limitation. Okay, with that information, I want you to answer the next question. Can you answer this question? I'll give you time. I want you to answer this with the reasons, okay? You want to justify. You should justify why you are selecting different cement for different applications. And this is our last question. I'll give you time. Yeah, we have more than enough time. I think we covered most of the things, theory in your lecture, but we can't cover everything in an hour. It's your responsibility for you to go through the lecture notes. Okay, it's very important and also interesting. When you look around, you will see the applications of this. So please go through the notes, because you have MCQ questions in your quizzes and final exam, which covers everything that you are learning. Okay, so massive dam construction. We don't want to gain the strength quicker, because it's not an urgent job. The heat is the problem, isn't it? Because it's a massive concrete, a lot of heat is generated, and you don't want that the dam to crack due to the thermal expansions and contractions. So that will be low heat. And how about the quick road repair? High early strength, yes. How about the sewage, sewer pipe, SR, sulfur resisting, and the bridge or overpasses, shrinkage limited, and the marine constructions. Okay, so that's all we have. Do you guys have any question? We have time. If you have any question, we can discuss. No questions? No questions? Okay. So if you don't have any questions, that's all from me. And yeah, you are free to go if you don't have any questions.